So it's a great pleasure to have today Herbert Spohn from the Technical University of Munich. And as you see, he will speak about hydrodynamic equations for the classical Toda lattice. Thank you very much, Herbert.
Yes, thank you, Claudio, very much for this very kind invitation. I put here IMPA, maybe that's incorrect. Maybe I should have put IMPA in Buenos Aires and Lisbon also. But anyway, I mean, so I put IMPA because I'm happy to talk about. I mean, IMPA is one of the sort of famous institutes for dynamical systems, and obviously classical Toda lattice is a classical dynamical system. But the aspects which I'm going to talk about is sort of a little bit orthogonal what people do in dynamical systems. But maybe it's still of interest to see that there are questions about such well-known systems which are of great interest. So let me see what I want to do. I mean, so I first have to move the screen. Yes, okay. So I prepared rather down-to-earth slides, and so maybe some of you know these things and others don't. I mean, so to them I'm talking. So let me first sort of do one slide on the Toda lattice. I mean, this was famous papers by Toda in 1967 and 68. And he discovered the system which I'm going to explain in a second. And of course, the surprising feature was that it's a system which has discrete indices. So you have discrete particles, they are labeled. And nevertheless, I mean, it has many conservation laws, and it's sort of presumably at the time is integrable in the sense of integrable classical systems. So this is why I call it sort of integrable many-body, to distinguish between integrable models like I don't know the Earth around the Sun. I mean, that's an integrable model, but here the emphasis is really on many-body. I mean, so the number of particles, the number of degrees of freedom is arbitrary. And Toda himself, I mean, he discovered already special solutions of the equations of motion, which sort of had soliton-like behavior. So he had a two soliton solution, and he could see how they sort of move through each other, and then they sort of emerge without maybe time delayed, but exactly with the same shape. And so on that basis, he guessed already that the system would be integrable, but the actual proof of integrability came only sort of like 6 years later, and I will come to what people found at the time sort of a few slides ahead. Okay, so let me first sort of tell you what the Toda lattice is. I mean, so you have classical particles. I mean, they have here an Hamiltonian, which has the usual quadratic kinetic energy, and then there's an interaction, which is not the usual summation over a pair of particles, but it's only nearest neighbor in the sense that the particles are labeled, and there's an interaction between two particles with neighboring labels. So the Qj, I mean, these are position and momenta. They are completely arbitrary. I mean, there's no constraint on them, but the interaction is sort of only between particles with neighboring labels. So here I've written sort of a sum, which you have to specify. And of course, there will be boundary conditions, but that's going to come. So let me just first write down the equations of motion, which, of course, they're just of Hamiltonian form. So you take change of momentum or sort of second derivative of the position, and then you compute the force, and it has this simple sort of sum of two exponentials. So rather simple looking innocent system. And I emphasize that in the literature you will find all kinds of coefficients, maybe the decay constant of that exponential, or maybe something in front, but then you realize that all these coefficients can be scaled out. And so actually this model has no free parameter whatsoever. Okay, it's just sort of the way how I've written. Now, of course, before Toda, I mean, there were already other classical systems where people discovered integrability. I mean, there were typically sort of classical nonlinear wave equations. And then there's sort of a huge quantum community which, have their own history. I mean, XXC models, Lieb-Liniger, Delta Bosegas, Fermi-Hubbard. There's also the quantum version of the Toda lattice. I mean, so that's a huge activity, and much of the kind of things which I'm telling you, they're actually motivated by many people working in the quantum corner. But for the purpose of the talk, my experience is that it would be extremely confusing if I would add any other model except for the Toda lattice, because try to understand this one model. I mean, then once you have this, I mean, then it's much easier to understand what's going on in the other models. If I start mixing the models, I mean, then you're totally lost.
Herbert, Milton is asking if 1D is important.
Yeah. I mean, so maybe I didn't emphasize this. So you see here, I mean, so particles are actually moving on the real line. So it's a one-dimensional system of particles moving in one dimension. Yes, correct.
That's important.
Yeah, very important. I mean, if I do, you could imagine to have the two-dimensional lattice. I mean, then you lose immediately integrability. So, I mean, there are few systems which are integrable also in higher dimensions that are sort of very much construed and strange. No, I think I can honestly say that all integrable many-velocity systems are in one space dimension. Okay. All right, so now just sort of way of thinking about these particles. I mean, so one thing is the Toda fluid. So these are, then I really think of these particles sort of, the Qj is the actual position of the particle. So they are sort of moving on R. And another way, which is sort of, suggested by writing the equation, the equations of motion, is that you can sort of think of this as a discrete nonlinear wave equation. So, if I replace differences just sort of, naively by derivatives, then you see that it's sort of like a wave equation with second derivatives over here, but with a very funny looking nonlinearity. I don't think anybody has really studied, the continuum equation. I mean, there are more interesting continuum equations which which people have studied, but not this particular one. Anyway, I'm also Toda. I mean, I'm thinking more about the second picture, but of course it's totally equivalent. All right. So the next picture which I want to show you is actually for the Toda fluid, and I want to sort of teach you one very important thing. I mean, so that's a very simple numerical simulation. So here's one running time, and here I have 16 particles which start at particular positions, and you see that these particles are actually moving on a ring or on a circle of size 20. Okay, so this particle is coming over here. I mean, here it's sort of it's plotted like this, but it's coming in on the other side, and also the whatever. I mean, for all these particles, they're really moving on the torus, and that's of course for the purposes of doing hydrodynamics, that's extremely important. But before that, just have a look at this picture. I mean, so here, for instance, you can see two particles. It's a very nicely two-particle collision, right? I mean, they're coming in, and then sort of they scatter off and move outwards. But then you see more complicated pictures. I mean, you see this string of many particles, and it's not so clear how to divide this into one or several particle collision. So the message is that the system is not dilute. It's not like the very dilute system where only sort of two particle interactions are important, rather than the system is sort of what we say strongly interacting, in the sense that there could be complicated interactions like this one. So for the hydrodynamics, it's important to have a non-zero density. I mean, just like in this picture, right? I mean, of course, eventually we want to do sort of space very large and things like this, but it's important that you have a finite density. I mean, the reason why I want to emphasize this is that in dynamical systems, there's a very famous paper of Moser, who studied also this system, but he simply assumed that the particles are moving on the entire real line. And then you have actually quite simple dynamics. You see, it's a repulsive potential. And then if I would continue these trajectories for very, very large time, eventually they would just simply separate and move along straight lines. And if I do the same thing at minus infinity, you see the same thing. I mean, they're separating and then they're moving along straight lines. And then you say, yeah, well, but what is the difference then between integrability and non-integrability? And that's sort of what Moser proved, and of course other people sort of knew this picture, is that when you look at the very large time asymptotic momenta, either to plus infinity or minus infinity, they are related in a very simple way, which is only true if I have an integrable system. Namely, as a set, I mean, they are simply identical. I mean, so you see the same outgoing momenta as incoming momenta, only their order is inverted. I mean, so if I order them here in a particular way, then you will see the inverted order, let's say in a particular way at time minus infinity, you will see the inverted order at time plus infinity. Okay, so this is something which is very well understood, but sort of it's nice. I mean, it's beautiful, but it's sort of speak of no interest to me because I really want to study the case where particles, you know, maintain a uniform density. Now it's a little bit more tricky than what I'm saying here because you see, if you take an integrable system and then you put boundary conditions, you might lose integrability immediately. Okay. Fortunately for the Toda lattice, that's not the case. If I put this on a torus or one-dimensional circle, then it's still an integrable system. Okay. I mean, this was understood by Toda already. Okay, so now the next thing I want to do is I want to talk a little bit about hydrodynamics. Of course, you know, the experts in the audience, I mean, who know this subject extremely well, yeah, you can do stochastic particle systems. Yeah, for this purpose, I imagine that I have a fluid in one dimension. So I want to talk here about the Euler equations. So the main point is that in the usual hydrodynamics, I mean, if I just take an arbitrary nice short-range pair potential, you will have three conservation laws. I mean, the number of particles, their total momentum, and their total energy. Okay, and under this condition, you can do hydrodynamics, and what you do is actually quite simple. I mean, you start with initial data, which you know, are called local equilibrium. So let me first sort of say what I mean by equilibrium and then by global equilibrium. So equilibrium is just what you learn from statistical mechanics. So I put here the grand canonical ensemble, so it's the exponential of the energy, and then there's the chemical potential, number of particles, and the total momentum. And the reason why I write down this formula, first of all, to remind you, but secondly, to emphasize that you know, the exponent is linear in the conserved quantities. I mean, that's a very crucial feature, and later on it will be also linear, but the linearity in the conserved quantities is sort of important in order to make any progress whatsoever. But this is what Gibbs told us, that should be of that form. And now local equilibrium is just something rather simple. So here, for instance, I put the inverse temperature as a function of x at some given at some given time. And now this is, you know, on a large scale, this is some smooth variation. And now I'm looking at one particular point here, which I call the macro point. And then I take a microscope and I enlarge, I guess here I enlarge by a factor of 10 to the 6, but if you take a factor of 1,000, I mean, that's perfect. And then, you know, I enlarge and I will see actually individual particles. And I can ask myself, what would be the statistical distribution of these particles? And the assumption of local equilibrium is telling you that what I'm going to see is exactly such kind of a distribution, only that I have to appropriate just these three parameters, okay? So now comes the two tasks which you have to solve. One of them is, you know, if you want to sort of write down the corresponding hydrodynamic equations, you have to do a little computation. I mean, you have to compute what are the average conserved quantities in this Gibbs measure here. So let's say the average density or the average momentum and the average energy and the average currents. I mean, so the currents, of course, I have not written down, but I will come to this, okay? So this is what I call the global equilibrium task one. This, of course, is something which you know, and for one-dimensional fluid, I mean, this is something which has been done many years ago, and it's sort of, you know, very well understood subject. It's very clear what the answer will be. So since it's not of importance to me, I will not give any answer. But what I want to emphasize is that there's then a second dynamical problem, which I call task 2, which of course much more difficult, namely assuming initially that slow variation in space, prove that you have also slow variation in space-time, and you know, these parameters, which depend now on x and t, are not just arbitrary parameters, but they are actually solutions of hyperbolic conservation laws, which then, if I use appropriate variables, would be the Euler type of equations. So this is task 2. Okay? And now let me sort of just emphasize that the task 3, I said already, is easy. Whereas task 2, for the model which I indicated, is very difficult. I mean, it looks extremely difficult because you would have to control this deterministic dynamics, and you cannot do it. But I should mention that there's a forthcoming, since 10 years, forthcoming book by Stefan Aola and Cédric Bernardin, who actually studied this problem. But the true Hamiltonian dynamics is too difficult, and therefore they add to the mechanical motion some stochastic interaction of diffusive type or random interchange of velocities. And then in this case, I mean, you can actually prove the validity of the Euler equations. Okay? So now I come to the hydrodynamics of integrable systems. Okay, so before I just talked about the hydrodynamics and the idea of local equilibrium. And now the idea is that why don't we try to write down the hydrodynamic equations for integrable systems? Now, integrable systems are characterized, if you want so, by an extensive number of local conservation laws. I mean, for non-integrable we have 3, but for an integrable, and I will explain for the Toda this in a little bit more detail, there will be a number of, the number of conserved quantities will be proportional to the size of the system. And so you might wonder, and then people have actually not really thought about this so carefully, except for, some sort of people who were very much foreseeing, like Roland de Bruch, so anyway, so the idea is that why don't we try? I mean, you try, and maybe it works, maybe it doesn't. Why don't we try exactly the same strategy as for simple fluids? Now, of course, there's a problem. We have a very large number of conserved quantities, and so it's not so easy to write down the hydrodynamic equations. And so this is why I put in my title, actually, the hydrodynamic equations of the Toda lattice, because what I want to convince you is that even writing down, what would be the correct equations is a somewhat non-trivial problem. Okay, so the task to, even for integrable system where you think that you have lots of techniques and then maybe you can do something, is still a very difficult problem. I mean, there are other integrable systems. Actually, there are some integrable systems for which this can be achieved, but in general, and certainly for the Toda lattice, I mean, there's no result whatsoever. And so actually in my talk, what I'm going to do is essentially I will talk about the statistical mechanics of the Toda lattice. Namely, I want to solve the problem number 1. I want to compute what are the average currents and what are the average values of the conserved fields. Okay, so the average fields and the average currents. The currents actually that's a very nice subject, but I just don't have enough time in this talk to really explain how this works. And I mean, for Pablo, this is something which actually came after Buenos Aires. I mean, that's a very nice proof of these currents. Anyway, so I will concentrate here on the statistical mechanics of the Toda lattice. So this is sort of like a little bit of a break in the talk. I hope you sort of understood what the problem is, and now we have to sort of move towards the solution and investigate the statistical mechanics of the Toda lattice. So there will be, for quite some time, actually almost all the way to the end, there will be actually no dynamics appearing anymore. It's really just statistical mechanics. Okay, and so what I told you is that for the statistical mechanics, we should be careful with the boundary conditions. And so now I'm really very careful. So what I do is I assume that I have n particles, so the J goes from 1 up to n. And the boundary conditions, it's not what you would expect immediately, but I mean, take this picture. So imagine that I have here one cell, just like in the numerical simulation with 3 particles, and then I'm just simply repeating that cell, right? And this is sort of what corresponds to periodic boundary conditions. And if I write this out in formulas, it means that the Qj plus n should be equal to Qj plus the size of your cell. And this parameter is actually extremely important. At the end, I mean, we want to do some random distribution, and we need a parameter which tells us what is sort of the average density of particles, and it's that parameter which controls the density. You see, I fix that length, and then I tell you how many particles I have, then I have fixed the density. Or the stretch, which is sort of the interparticle distance. And for the momenta, I do the standard periodic boundary conditions.
Herbert, another question.
Yes.
So Milton is asking again that if in Bernardin Aula, they put noise that conserve the relevant quantities. So he's asking,
because
is there a canonical way to put noise preserving most of the conserved quantity in this model?
Yeah, this hasn't been. I don't know. Okay, maybe Pablo knows. I don't think it's totally trivial to actually invent the noise which does that for you, right? I mean, you see, for the case what Stefano did, I mean, they basically had sort of diffusive three-body collisions, or they had sort of this interchange of momenta. So yeah, you're completely right. I mean, that's conclude in such a way that you conserve the quantities which you expect are anyhow the only conserved quantities if you do the Hamiltonian dynamics. I don't think this has been tried for an integrable system, at least to my knowledge. I mean, that's a good question. I don't know the answer. Okay, so now I come to slightly more technical, the way how you can deal, with the statistical mechanics, and of course I have to rely on the proof of integrability for this system, which goes back to Flaška and Manakov. Independent Manakov is in Novosibirsk. I mean, that at the time was sort of a center of dynamical systems, at least sort of from the sort of, I guess, more theoretical physics side, but Manakov was part of that, and Flaška was at the Courant Institute, was in Paris. So anyway, so it's called Flaška variables because he sort of realized, talking to people at Courant, what he should do is he should look for a lax matrix, and in fact, that's rather easy to do. I mean, so you introduce the difference in position, which I call Rj, and then sort of the square root of the interaction potential, which is called Aj. Okay, and then once you had this idea, you just write down the equations of motion, and you see that now you use a little bit physical intuition. They look more algebraic. I mean, it's sort of just quadratic nonlinearity, and you also see that if you think of a lattice, I mean, here you have a coupling to the right, and here you have a coupling to the left. Okay, your phase space is now R plus. This comes from the A, and R from the stretch, which has no restriction. Okay, and so here is sort of the lattice picture now. I have periodic boundary conditions. Now it's the usual periodic boundary conditions, and so you have sort of like a lattice, and then you have interaction between neighboring lattice points. Okay, so it's a lattice field theory if you want some. Okay, now the conserved quantities. Well, so here's one conserved quantity, namely the stretch. So if I sum this from 1 up to n, and now I take the time derivative, I took a particular simple example. If I took a time derivative, then you see that it's pj plus 1 minus pj. And so that's a finite difference form. So this is what I mean by a local conservation law. Okay, and it's local because the field, the Rj is local, it's just sitting at side j. And also the current, which is here the difference. I mean, so the currents would be the minus pj. That's also a local quantity. Okay, but now the claim is that that there's not only this one, but there are many, many more. And so how do I get all the other ones? And this is what you learned from Flaška. And he was telling you that there's a simple construction, which is based on what is called the lax matrix in this business. And I've written this down for the periodic boundary conditions. So you arrange all the momenta along that diagonal, and the A's, the exponential of the stretches, you arrange them at the first off diagonal, and since you have n of them, I mean, you put them right in the corner, and that corresponds to periodic boundary conditions. And then there's associated B matrix, which is anti-symmetric, which looks like this. And then, it's just really, I mean, once you know what you do, it's just a few lines to convince yourself that rather looking at the mechanical equations of motion, you can write down this matrix equation, which is perfectly equivalent to the equations of motion, which I've written just in the previous slide. Now from this, since this is anti-symmetric, you realize that the eigenvalues of L are conserved. So if I compute an eigenvalue, that will be some complicated function of the piece, but at least sort of, you have a nice equation to look at. You find that the eigenvalues are conserved. Now, that's no good. I mean, of course, it's very good, and this is what Henon did, and of course, it's absolutely superb work. But for hydrodynamics, it's not very good because the eigenvalues is highly non-local. It will depend on all the variables. And if I change one of them, I mean, then the eigenvalue will move all over the place, right? So the eigenvalues are conserved, but they're not local. But this is what Flashka told us also, is that once you have this construction of the Lax matrix, you immediately see how to construct local conserved quantities. And the mechanism is extremely simple. All what I have to do is I take the nth power of the, I mean, Ln is the size of the system, little n power of that matrix. Okay. And if I write out, and then you take the trace, so that's the number. And if you write out the matrix elements, then you sum from 1 up to n, and here's the JJ matrix element. So you see that's obviously a density. So this I call Qj, the density of that particular conserved quantity. Okay, now, of course, this depends on all variables, but the Qj should be local. That's what I mean by having a local conservation law. Now, how do I see this? Well, I mean, fortunately, it's very easy to see, because you just start expanding your matrix out in, you just expand it out, and you see that you will get a big sum, but the sum is labeled by a random box. I mean, it's a triangle matrix, and therefore you will have a random box which can go either up, down, or stay constant, and then you have to do the sum over all this random box. But that's obviously local. I put just to make sure that everybody understands. I make a simple example. So in this sum, let's say I put n equal to 6. There's, for instance, this very particular random walk. And if I ask myself, what is the polynomial which corresponds, or mononomial which corresponds to that, then this one is an A0, and this is also an A0, so I get A0 squared. Then from these two, I get the P1 squared, this one and this one, and from this one is an A1 squared. And so you see, it's obviously a local quantity. Okay, and so of course it's a big sum, but it's still local. I mean, I emphasize that. You see, if you take non-local things, then hydrodynamics becomes very murky, and all these arguments about local equilibrium also, they might be still true in some way, sense, but it's not so clear. But local is fine. I mean, it's strictly local. And so you see that if I go up in the index, of course, the support of this density will start increasing as I go to higher and higher n. But for each n, it will be local. And then, of course, you just do the derivative, and you verify that it has finite difference form. You get the local current, and you get also a nice formula for the current density, but I'm not going to touch that. I will just sort of work with these conserved quantities. Yeah. Okay, so step one, we have found the conserved quantities, and we have, fortunately, maybe not completely simple looking, but nevertheless, I mean, a very concrete description of what they are. So the next thing is statistical mechanics. No. The next thing is statistical mechanics. So here I put Boltzmann because, you see, I want to tell you what you should do in principle. I mean, this is an integrable system, and it's bounded. There's no scattering, and so we know that the phase space will be foliated into invariant tori's of dimension n-1 if you do the counting. Okay, so you have this big 2n dimensional phase space foliated into tori of that particular dimension, and on the tori you will have a quasi-periodic or almost periodic motion. Okay, and you have enough control over the action variables to know that actually almost surely there will be no coinciding frequencies, and therefore in the long time limit, if you do average over some smooth function, you will actually go to the Lebesgue measure on the tori. I mean, this is a result of Enrici and Trappeler. So that's a real theorem. I mean, they analyze this very carefully, and you can look up and you see that you have enough control that you can sure if I fix n, then in the long time limit, you will end up with some uniform, of course, depends on the initial condition, but you will end up with some uniform distribution over the tori. And this is what Boltzmann told us already many years ago, that this is what should be happening. But I cannot use it technically. I have no idea how to, I mean, of course, it's a well-defined measure, but I have no idea how to do prove anything about this measure. I mean, these tori's are somewhat complicated in phase space. I just don't know what to do with them. Okay, and so I do what people in statistical mechanics do very often. And in some cases you can justify, and in other cases you cannot justify. So in our case, I mean, it's certainly not justified, is that you use, something which people call the equivalence of ensembles. And I just want to show you in one simple example what this means. So, I mean, for instance, I said that the RJs I mean, the sum of stretches are actually fixed to be equal to NL, right? I mean, so this is one constraint which defines this invariant Toda, right? But I don't know how to deal. That's a very easy constraint, but the other constraints are more and more complicated. I don't know how to do. But now you say, okay, rather than taking the uniform measure according to these constraints, I mean, you replace this by the exponential. And so rather than looking at this measure, you look at e to the minus PRJ, and P is sort of, you know, the dual to that thing, to the length of the size of the system. And so this would be sort of, you know, the microcanonical, and this is sort of the grand canonical prescription. And of course, you know, that's a whole large series of large deviations, which tells you under what conditions such kind of identities are true. But for our purposes, I mean, you know, I just have to assume it. And you see that that's very nice, because I have this exponential interaction potential, which was repelling. It looked like it's a decaying exponential. But now I get this extra factor from this constraint, which is sort of linearly increasing. And so both together sort of will give you a potential, which is, you know, increasing at plus infinity and increasing at minus infinity. Of course, the pressure for this to be true, you see the L has an arbitrary sign actually, but the pressure has to be positive. Otherwise, you know, this would have the wrong sign, and you get an unstable system. So the pressure, this is physically the pressure. It sort of tells you how much from outside you compress the system. And therefore, I get a nice a priori measure, which is a product of the momenta. And then there is sort of this Flaschka variables, which I call DHA. I mean, they have a volume end, which is this 1 over HA. And this one you see is nothing else but HA to the power 2B. And people who know about probability, they see already that looks like a chi distribution. And of course, the chi distribution will come up, right? I mean, there's still the Gaussian missing here. But okay, so this is my a priori measure, and you can check directly that this a priori, so that's sort of the analog of the Lebesgue measure. You can check immediately that this is actually invariant under Toda flow. Okay, so this is sort of the a priori measure. Now I have to weight it, just like what we learn in our statistical mechanics course. We have to weight it. Okay, so let's see what the weight is. So now I hope you still remember that I emphasized sort of 20 minutes ago that when you do Gibson statistical mechanics, then you look at the exponential of a linear combination of the conserved quantities. So let's just do the same thing. I mean, so here I take some large kappa just to make sure that I don't have to worry about infinities. I put here, you know, for each conserved quantity, I put here chemical potential, which I call mu n. And then I just copy my definition. It's trace L to the n. But you see, if you pull this sum into here, I just get a function of that matrix. And so I can also write it as e to the minus trace of a function of that matrix. And of course, you know, this function is sort of defined by what I've written. It's just sort of a power series expansion given over here. Okay, but you know, maybe this power series expansion is sort of more like way how we write it down. I mean, maybe I should not take it over seriously. What I really should take seriously is this formula, and you know, this function I call the confining potential. I mean, so it's a useful name because you know, if in order to have an integrable Boltzmann weight, you can see that what I actually need is that this potential has to increase at infinity. How much it has to increase at infinity, you know, we don't know at the moment. Well, we know a little bit, but we don't really know so well. But you know, it must be of this type. I mean, so here, you know, I put a simple function like x squared plus maybe up to the polynomial of order 4. But in general, it will be more complicated. Anyway, so now we have a function which characterizes the Boltzmann weight, which is this confining potential. And on top of this, maybe I just switch down here. We have also one parameter in the a priori potential. So I mean, you know, this is just terminology. I mean, people call this generalized Gibson, and everybody in this community, if they say GGE, I mean, then they know what they mean. Anyway, the GGE here just means sort of, you know, the Gibbs ensemble, which I should use for that very particular integrable system. And so we have now two parameters. One is a function, which is not so surprising because they have an infinite number of conservation laws. So that's this function V, and then this function V is sort of fixed. It doesn't depend on n, it's just given. And then of course there's still a scalar, which is the pressure. And so here I've written down now in full beauty sort of my finite volume, you know, a lattice of n sides with the a priori measure, which is given over here, and then I have the exponential of minus trace of some function of that Lex matrix. Okay. All right. So this is the quantity which we have to study. Okay. Now let's make one example which I think is sort of instructive, because it sort of foresees already, what is going to come later. But before doing more technical stuff, I mean, I think that's a good moment sort of to actually explain what's going on here. Let's look at the thermal case, right? I mean, so the thermal case is just a quadratic case, right? I mean, so you think, that must be very easy, okay? So it's just beta times W squared. That's the thermal case, okay? So then you just have a Gaussian weight, okay? Now you see what we want to compute is actually, you see, I want to do expectation of these conserved quantities. So I want to compute sort of functions of Ln, and so this means that no, sorry, maybe I shouldn't say this. So let me first say what is written. I mean, so before doing any analysis, I mean, so you see, under the Gibbs measure, this matrix becomes random, right? Because the entries are now distributed according to that very particular measure. And so in the thermal case, it would be sort of, this very particular form. And then you see that in this case, I can say explicitly what that distribution is. It just means that I look at the random matrix where the diagonal is IID Gaussian. I mean, it just comes from this factor here. I mean, the squared has two terms. It's the PJ squared and the HJ squared. And then, the HJs, as I sort of try to mention already, now I have the Gaussian factor is simply IID chi distributed, and the parameter is this 2p. Okay, so this, for the thermal case, you have a rather simple looking random matrix, but still, even in the thermal case, we want to compute something which is non-trivial. I mean, we want to compute the expectation value of the conserved quantities, and this means to compute basically powers of trace L to the little n, and that's something which is even for this thing is non-trivial. Right? Okay, so now let me sort of see what I have to do next. Okay, so maybe I should say a few words about what we want to know. I mean, one thing is sort of the more statistical probabilistic question about measures exponential mixing. Let me not go into this because otherwise I'm going to lose time. I mean, we can compute the free energy, but let me sort of come to the central object which we actually want to compute. You see, the quantity which we maybe I should go to this particular formula here. So this is I put here lattice side 1. So I take the density at let's say at lattice side 1, and I look at the nth conserved quantity, right? I mean, and I want to compute the average values of the conserved field. I mean, this was one part of the task. It was fields and currents. Currents, I don't care. Now it's just a field. So it's Q1 to the power n. And then I have to do this horrible expectation here, right? But you see, it's not so very hard, because I can use the fact that this is sort of, the trace of L to the n. And therefore, I can rephrase this sort of in a sort of much more intuitive object. And so let me do this. So what I want to do is I want to look at what I call the Lex density of states, or as probabilists you would call this the empirical density of states. So here are the eigenvalues, and then I just take here this empirical sum. So this sort of gives me what people in physics call the density of states. I mean, it's just the empirical distribution of the empirical distribution of the eigenvalues. Okay, so this is a measure which is normalized to 1. It's just sum of delta function. Okay, and now the assertion is that under this Gibbs measure, this is random because the lambda j are random, but under this generalized Gibbs measure, this will converge, and that's actually 0, will converge to a deterministic limit almost surely. And so once I know this, then this, if I just do the translation, this means that this expectation value will actually converge to the nth moment of this limiting Lex density of state. Right? And so you see that central object are not so much the conserved quantities. See, after all, it's linear. I mean, I can take combination of two conserved quantities, I still get the conserved quantity, but it's sort of like a moment problem. I mean, what I do here, I just have written down the moment problem. The actually crucial quantity is really the density of states. And this, you know, time is always running. This I sort of want to sort of explain you in a little bit more detail why this is important insight in terms of this you know, hydrodynamic limits. So let's sort of go back to slide 1. And what I told you is that sort of, you know, I have the system, maybe I have, think of a numerical simulation, maybe I have 10,000 particles, but, you know, I see this wobbling back and forth and has no particular structure. So what I have to extract from that picture of wobbling trajectories, I have to extract those quantities which have a slow variation, both in space and time. And what this formula tells you is a very simple procedure. So I just look at a block, let's say, of 300 particles, okay? In this block, I form the local X matrix according to that definition. Maybe I should really go back and show. I form this very particular matrix with n equals 300 for that very particular block of my large system, okay? Okay. Now, I'm looking at this block. I have this 300 and 300 matrix, is still wobbling. But now I look at the eigenvalues of this matrix. And then the assertion, I will get a rather smooth function. And when I look at the neighboring block, I will see a similar smooth function, which of course is not exactly the same. And if I go a little bit further, I will see also a rather smooth function. And so the claim is that it's the local density of states which will satisfy a PDE of conservation type. This is what these formulas tell you. So you know, it's a very different way. You forget about looking at specific particles. I mean, you just look at the density of states. Let's look at the distribution of the eigenvalues of the X matrix locally, and this will be the slowly varying quantity. Okay, so now let's see. How much time do you have?
10 minutes, but we are not very strict, Herbert, so it can take longer.
Okay, so now I want to sort of tell you, you know, one thing which I'm proud of, because sort of I discovered this myself and sort of somehow got the whole story going. And so let me just use a little bit of time to explain this. Okay, so now we want to compute, let's say, something like the free energy. So I've written down for you the free energy again in full glory. So here's the free energy. I have this two n integrals, well, 2n-1 integrals. And now I have here sort of, you know, this a priori measure, but now I did something, and here was trace v to the ln. But now I do something which actually goes back to Dumitru and Edelman, who looked almost at the same thing. I mean, so their matrix, okay, they're called B and A's, I mean, just instead of P's. I mean, their matrix looked like this, that they didn't have this often angle term, which doesn't play a big role. I mean, this is why I have 2n-1 here. But they were not looking exactly at this thing, but you know, what I want to look at is then the exponential of the trace of a slightly modified matrix, namely the one which I've written here, and T is sitting over here, okay? And so you see that when I look at this matrix and when I look at the a priori measure, then you see that the off-diagonal elements are really sort of, if I put here this exponential weight, are really quite distributed, okay? And now what Dumitru and Edelman tell me, so this is a very complicated formula, you know, I have no idea what to do, but what they discovered in a totally different context, which I cannot go into, they discovered that they actually are able to compute the volume element. So, you know, they can make the transformation from the A's and B's to the eigenvalues and other parameters which are integrated out. And the final thing, what they find is actually quite simple. Namely, what they find is a formula which looks much simpler, because if I only n-dimensional integral, the lambdas go over Rn. And now I have a weight which is the exponential of v of the lambda j. This comes sort of basically from this term over here. You know, you should think of representing this object in terms of eigenvalue of this matrix. So this is what I get from this term here. So that's fine. But then, you know, they are able to compute the volume element. And the volume element, lo and behold, comes out, this is an exact identity for fixed n, comes out with a parameter beta here. This is the parameter beta over here. This is the parameter which appears here. And it's beta over j times sort of, you know, the pairwise sum over this logarithm. So this is something which is very famous in statistical mechanics of integrable system. That's so-called log gas, because you have a confining potential, and then you have sort of a logarithmic interaction between pairs of points, if you want so, right? I mean, point particles. I mean, this is called the log gas. I mean, you can find there's a sort of like almost 1,000-page book by Peter Forrester, who basically studies all kind of properties. Lots of people have worked on this. So this is sort of a very, very well-known, understood topic. Okay. But now there's this parameter beta, and then there's another thing which is sort of very unfortunate. This is not what I want to do. You know, I have here, this is a pressure which is varying linearly with this with the lattice side. It's beta times J. Beta is just any positive number, whereas I want to have the case where it's constant. So it's totally useless. It's a nice formula, but I don't know what to do with it. Okay, because you know it's close, but it's not exactly what one has to do. But now you see that you know, I mean, nature is not so unfriendly. I mean, what you realize after while looking at this formula, what I should do is I should make this slope slowly varying. So I choose the beta to be 2p divided by over n. Then you know, this sort of has sort of somehow the wide values for j equal to n. But otherwise, you know, it has a slope like 1 over n. And so locally, it will look like a constant. And in fact, I get a problem which is usually considered and is in fact much simpler than the standard log gas, which is the one which I've written here with the fixed beta. You know, my beta is now varying like 1 over n. And so it's something which is called the mean field sort of log gas. And so since I have mean field, it will be very easy to figure out what happens in the large n limit. Okay, and I have to pay a little price, namely, you see, I mean, you know, as I go through this linear ramp, I have to sort of sum up all the contributions of my free energy of the Toda system. So what I get is actually this integral from 0, 1. This is the Toda free energy, and this is the quantity which I get when I take the large n limit of this one. And this one is sort of very easy to understand. You see that you know, it's sort of written almost directly in terms of the empirical measure. You know, this is just the empirical measure integrated over the confining function. This is just sort of a quadratic term in the empirical measure. And so you can, and I have the 1 over n, so this sort of just balances. And so you can immediately figure out what this quantity would be in the limit. And I guess this is what I've written down in the next slide. So you see that you find a nice free energy functional, which is here is the confining potential. This comes from the interaction. And this is the entropy term. And then the assertion is that, you know, this functional has a unique minimizer under the constraint that the empirical density should integrate up to 1. Once I have this unique minimizer, then I'd have to sort of do this derivative according to the prescription of my formula. So if I want to get the Toda free energy, I have to take this mean field energy evaluated at the minimizer, and then I have to take the derivative with respect to p. The p sort of sits over here in this functional. Okay, so it's a little bit involved, but it's very explicit. And of course, if you really want to compute what the minimizer is, you will have to use the computer or so. But nevertheless, I mean, it's a very, very concise formula. And here I've written down what the corresponding formula for the minimizer is. It's again a derivative, right? And so just to, yeah, maybe I have so much time. Just to give you one example, I mean, so now I take again the thermal case and I put the inverse temperature equal to 1. And now I want to look at what this minimizer looks like as a function of p. So when p is, when p is very, very small, so particles are extremely far apart, then all the a's, the off diagonals are 0. Along diagonal, I have unit Gaussians, and so the empirical density of states will converge simply to a Gaussian. So that's the one which I have put here. But then when p goes to infinity, it's sort of a little bit more tricky. I mean, so you have to do some analysis in order to see this. So, you know, when p goes very, very large, I mean, then actually what happens is that you know, the system remembers that I looked at sort of a mean field problem, and you know, there's another problem which is not mean field like. And for the non-mean field like, if I just fix beta and not put 1 over n, then one knows that in this particular case, the empirical density of states is actually given by the Wigner semicircle law. And now I have to take this derivative, and from this you conclude actually that when you look at asymptotic density of states in the limit SB goes to infinity with scaling, really looks like sort of a distribution which sort of diverges at 2p with the square root. And of course, you know, it diverges, but still it's a very nice integrable function. And of course, if I take p not really into infinity, what's happening is that, you know, it diverges for a long time and then it sort of shifts over and sort of, you know, immediately decays. You know, I mean, for any p non-zero, the rho q will have support the infinite line. I mean, that just comes from the entropy term. I mean, that sort of is strong enough to sort of smoothen this out. Okay, so this is what I wanted to tell you about. So that's the last slide. So this is what I wanted to tell you about how to compute the average values of the fields. I mean, so you see that for the Toda lattice, it's related to a particular free energy function, and that's actually a rather universal feature. I mean, also other systems, other integrable systems have the same structure. But now, you know, since I put the hydrodynamics in my title, I just want to explain you that you see one slide, how complicated or how non-complicated these hydrodynamic equations are. So let me sort of write down for you the hydrodynamic equation. So here is again my macro point, and now I have to, there's a density, so it's a stretch, and then there's also the local Lax density of states. I mean, so this comes from the Lax matrix, and that's another parameter which I told you is inside my Gibbs measure, right? I mean, it's the P or the dual of the pressure. And so this one is easy to write down. I mean, that's just sort of the conservation law of mass. And the Q1 is the first moment of this density of states of the Lax matrix. And here I've written down for you the evolution equation for the density of the Lax matrix. So it's just time derivative of that Lax matrix. It's a conservation law ddx, but now comes some somewhat horrible object. I mean, this is sort of the current as a function or as a functional of rho, q, and nu. This is not very explicit, and so you know, maybe you want to know how complicated that function is. Well, okay. I mean, you know, I've just written down something which you will not be able to understand very quickly. I just sort of put here the formula so that you're convinced that I can write down something. Right? Here I've written down this equation again, sort of. I don't know. That's normal form. That's not so important. Okay. So the main point which I want to make is that essentially you have to invert an operator, right? I mean, so here's an operator which has this logarithm, and essentially you have to sort of compute the inverse of that operator. This you will have to do numerically, unless in thermal equilibrium. But in general, you have to do this sort of numerically. So the way how this goes is that you know, you evolve. If you want to do sort of numerics, you evolve the rho q a little bit, and then you have to solve, you know, this inverse of the operator in order to get the updated currents, and then you just sort of keep iterating this. Okay, so I mean, there are a few cases where you get analytic solution, but in general, I mean, you have to rely on that. These are rather well-behaved operators, so it's numerically not such a difficult thing to do, and then you can do such simulations. You know, I have co-workers with did these simulations, and you can actually really compare, you know, the full microscopic dynamics of the Toda lattice with the solution of these hydrodynamic equations. But this is, since I'm going over time, I mean, this is sort of something which I also have not prepared. I mean, that's sort of a different story, and you know, if you really want to understand, I would have to go into more detail. But I want to give you sort of like a visual impression, you know, what really these hydrodynamic equations look like. So I emphasize, I mean, this is what sort of something you might keep, is that it's sort of a system of a scalar and of a function. The scalar is simply, you know, what is the average distance between particles, so that has a very easy meaning. And this is sort of the big discovery. It has sort of not an intuitive immediate meaning, but when you look at the Lax matrix, I mean, it has a very nice look. It's the local density of states of your Toda lattice. Okay, so let's see what I have said here. So there are, I mean, if you want to know more about this, of course, you know, there's huge work on quantum many-body, which you know, one has to sort of study if one really wants to understand this. But I mean, if you really want to get a little bit of a feeling, I mean, there are nice lecture notes by Benjamin Dalion about a little bit about Toda, but mostly about quantum many-body systems. I mean, he makes the point of you know, how similar these hydrodynamic equations looks like for distinct integrable many-body systems. So this, if you want to understand that point, I mean, these lectures are fine. I've posted something which covers essentially, well, a little bit more, but you know, the kind of things which I told you you can find sort of in a more pedagogical way in this article. So I emphasized already that the Euler equations for different systems have always the same structure. I mean, so, you know, if you look at the box-ball system, it has the same structure. And if you look at the Lieb-Liniger delta Bose gas, the Euler equations have the same structure. So in that sense, I mean, you know, these Euler equations actually are a rather general property of integrable system. And I should mention that, you know, physicists are always busy to sort of, you know, sort of find new things and consider this to be as a closed chapter, which I don't think so. I mean, you know, there are many open questions here, but they are sort of course curious. And in fact, in the literature, you can also find Navier-Stokes correction. So this is sort of in the density expansion, the Euler were first order derivatives in dx. And if you look at the Navier-Stokes, I mean, you will get second derivatives in dx. I mean, it seems to be perfectly well defined. Anyway, so thank you very much for listening. I hope I could cover and give you some feeling for what I was promising you in the title. Thanks. Thank you.
Well, thank you very much, Herbert, for this very nice talk. Well, you can unmute your microphones and applaud if you wish. So now we are open for questions. So is there any question? So maybe I can start with one. If you go back one slide, Herbert, and then can I understand this scattering shift as an equation of state? I mean, for in your model, so that you're expressing your current in terms of these densities.
Okay, maybe I first tell you what scattering shift means, right? Okay, so scattering shift means the following: that if I take two particles just on the infinite line, and then I told you that when I look asymptotically for large time, they will just move linearly, and the same thing if I go backwards in time. Okay. But now to that linear order, to that linear motion, there's an order one correction. And it's that order one correction which is this logarithm. So if I have two incoming particles, one with velocity v and the other one with velocity v prime, and I do the scattering, and then I subtract the linear motion, the assertion is that what I see is that very particular quantity. And now, what Moser proved is that when you now take n particles, you will see exactly the same structure. Of course, then you have to sort of add up the shifts, and I would have to draw some pictures in order to convince you. But the point is that when I take n particles, and then if I look at the order one correction, it will be still determined by this logarithm. So this T operator is sort of a priori defined really in terms of the scattering dynamics, and what people predicted already, but which comes also here in my talk. You could see that the logarithm appeared in this formula which I showed you for the free energy, right? It appears over here. And if you would ask experts on this hydrodynamics for integrable system, they would say it has to appear there. It must be there. It's part of the general structure, right? I mean, that the free energy functional which you write down must involve the scattering shift. And the reason why they are so convinced is that they have already in the delta Bose gas, the Lieb-Liniger model, I mean the Yang paper, I mean they found already the fact that this quantity appears in this dual feature. I mean, as part of the statistical mechanics of the system, at the same time in the scattering problem. And it would be nice if I could understand this sort of, if I could make this connection more directly. Here you see, the way how the logarithm appears is through this computation of Dumitru and Edelman, right? I mean, they were just working out volume elements. I mean, they changed variables and to one, they computed, how you go from these volume elements to this, to this volume element to this volume element, right? I mean, so there it looks like, sort of like a mathematical derivation which a priori, sort of comes out of this computation. There's no reason for them. I mean, it could have been differently, so to speak, right? But the claim is that these two things are intimately connected. So I have not answered your question actually, but what I want to say, let's see. I mean, okay. Okay. So the point is that so this T operator, plays a very important role in when you. Maybe I could explain it in the following way. You see, you have this free energy function. I mean, you have a large deviation function, so to speak. And of course, one way to analyze this large deviation function is to linearize around the minimum. Okay, and if this now becomes an operator, right? And if you linearize about the minimum, I mean, you will see immediately the C operator appearing, because before you had this pair interaction, and when you look at this, let's see, maybe I can show you. Yeah, when you look at this object here, and if you start linearizing around the minimizer, then of course you will get you have to linearize this object, and that's already the T operator, right? And so the assertion is that this operator will play an intimate role in this whole business, and of course also in the way how you get the hydrodynamics. Okay, so and maybe I cannot say more, but maybe these are some explanatory questions.
Well, thanks. Any other question?
I have a question. Herbert, when you talk about these effective speeds, are you talking about the same particles that you showed the picture in your second slide?
Yes. Let's see. Yeah, no, I do. So let me make sure that
the picture.
So yeah, the picture. Okay. Now, well, I mean, okay. So here, of course, let's see. At one given moment, I have a set of P and Qs, right?
Yeah.
Okay. So from this set of P and Qs, I can form the Lex matrix, right? So I do the P's along the diagonal, and then I have to put the potential difference at that particular moment. I have to take the exponential and I put this in the off diagonal.
Mm-hmm.
And then I have a tridiagonal matrix, and I compute the eigenvalues. That gives me the density of states. So yes, of course, I cannot, my eye cannot do that, right? I mean, and your eye also not, right? But as a mathematical description, this is what I'm trying to say. I mean, when you look at this picture, it's very hard to figure out, what are the slowly varying quantities. I mean, they're all sort of varying of order one, right? Of course, maybe they don't look so chaotic, but anyway, it's in one dimension, and no, it would be very difficult, right? I mean, if I just look at the picture, I cannot see it, right? But the point is that what the beauty of this Lex matrix is that when you do this operation, which I just told you, I mean, then you really get quantities which are slowly varying, right? I mean, so here, I mean, this is just some given small simulation, but if you would sort of, for instance, run this for a little bit longer time, and then you do some averaging, I mean, then I think you would see, this density of state, which you compute from the free energy function. I guess a small system and things like that. I mean, but and then we have done such simulations. I mean, that's yeah. I mean, the numerical simulations where you can see these are typically of order maybe 2,000 Toda particles, but there you can see this very well, right? I mean, there's no question about that. So that's sort of the nice thing that the Lex matrix is not only giving you the eigenvalues or the conserved quantities, but gives you also the mathematical object which enters into your hydrodynamic evolution equation. Right? Because a priori, sort of this. So okay. So it's like you look at at average values, I mean, it's just sort of a sequence of numbers. When you realize that there are moments of some probability measure, then you're sort of in much better shape, right? And because then you have an object which you can actually look at, right? And it's the same thing here, right? If I just look at the moments of the conserved quantities, I mean, it's fine if you want to do the definition, but you know, it's just a big sequence of numbers, right? I mean, what do I do with that? But when you go to the Lax matrix, you know, it's really the density of states which is sort of involved. Okay.
Thank you.
Just words, but I hope it clarifies. No. I mean, it's there. Yeah.
Well, any other question?
I have a question.
Yes.
So, Pablo was explaining to us about this hard rod system like 2 weeks ago. And so the final equation, the hydrodynamic equation, looks structurally similar to what you were describing. Not the same, but similar. And so I was wondering if you can get, so there are 2 questions, whether you can get that model or other meaningful model by taking a limit of this Toda system, in, like, for example, take Q very big and then the exponential becomes a hard wall, or taking maybe at the hydrodynamic level, taking the hydrodynamic equation, maybe you can take some limit and get some simplified equation.
Very good question. No, neither one. I mean, if you look in the book of Toda, of course, you know, it discusses the hard rod limit. I'm not sure. I mean, of course, one could try. It looked to me sort of like a singular limit, but the truth of the matter is sort of slightly different, at least sort of the way I look at it. I mean, but it's a very good question. I mean, so let me, I have to show you what it is, okay? Okay, so you see, you look at this T operator, and now I explained to you what the scattering shift is. Now try to compute the T operator for the hard rod system. Yeah, you see, they do the shift, which is just the length of the hard rod, and it's totally independent of the incoming velocity. You see, if they come in very quickly, you know, how much they're shifted is just the length of the hard rod. So you see, this T operator becomes now a very simple one-dimensional projection operator. It's just the integral over that function, right? Now it becomes now just a constant function. It's just minus a. And so you see now once this operator is just a projection operator, then I hope you teach this to your students. I mean, you can take inverses very easily, right? Okay. And then you go through this formalism, you look up what your equations are, and lo and behold, you get exactly the equations what Pablo was telling you, and of course the ones which Dobrushin was actually proving many years ago. So the hard rod system is the only model for which, well, maybe boxing ball. I mean, then you know, this is what Pablo understands. I mean, so maybe I shouldn't stress it so much. I mean, box ball is sort of also very close, but anyway, I mean, you know, the hard rod system is a beautiful illustration of the general feature over here, but it's sort of too simple in the sense that you know, you don't have this dependence anymore. And you know, when I first heard about these things, you know, these quantum physicists are, of course, you know, I mean, looking at hard rods, I mean, that's very far away from what they are thinking about. But when I told them about the hard rod system, they were extremely happy, because now they understood many of the formulas which they are writing down in a you know, very simple model where they could sort of really understand what the various objects are. And the hard rod model has now become sort of, you know, whenever they give a lecture, well, now it's already 3 years ago, but still, you know, they still do it. I mean, you know, they sort of, when they try to explain how these formulas appear, then typically they take the hard rod system, you know, what it means, the T operation, and all these kind of things. So no, I mean, the hard rods, I mean, it's a beautiful example that the structure is the same for various integrable systems, yeah. And the true point is, so for the hard rods, you don't need any variation problem, because, you know, your free energy is sort of very simple, right? But the T operator is still there, and then T operator you need in order to write down this equation. So yeah.
Thank you.
Thank you. So any other question? Well, so if not, let's thank Herbert for this very nice talk.
For listening, my pleasure. I mean, so yes.
So thank you very much, Herbert. Well,
Okay. Have a very nice day.